Hi, everyone. My name is Chelsea Finn, and I'll be talking about some of our research on how language models make stuff up and what we should do about that. So, as motivation, machine learning has been deployed quite widely, especially in scenarios where getting the right answer isn't critical. For example, in recommender systems where you just need to recommend things that are going to be helpful and useful and interesting to users rather than the exact best thing that should be recommended. Machine learning is also quite useful and has been deployed widely in scenarios where getting the most common use cases right is pretty useful, such as in Google Translate. And it's also useful in cases where the goal is really to make an expert faster, such as in code generation in Codex. And arguably, machine learning has been really successful in all of these scenarios. But at the same time, we've also seen examples where machine learning models have fairly important and critical failures. For example, if you tell a former version of Bing Chat that today is in 2023, it will try to convince you that today is actually 2022. It also somewhat notoriously tried to convince a New York Times reporter that the New York Times reporter was married but not happy in his marriage. And I think that these sorts of kind of failure modes that we see come up can happen in a few different circumstances. The first is when their inputs deviate from the training data, essentially when there's a distributional shift between training and testing. The second is when the model underfits to the training objective. And the last scenario is if it is actually fitting its training objective well, but it's not doing so in a way that is actually aligned with the kind of behavior that we want. Essentially, when it isn't penalized enough for making up answers or for making mistakes. So this kind of observation that machine learning models make stuff up, this is okay in some scenarios. In some scenarios, we actually want these kinds of models to make stuff up, such as when we want them to generate a dragon fruit wearing a karate belt in the snow, or generating an image of teddy bears swimming an Olympic swimming event. But in other scenarios, the fact that models are unreliable when they're deployed can actually be pretty problematic when those models are interacting with real people. For example, when news sources are actually using these systems to write articles, when mental health companies are trying to actually use this to talk to people with mental health conditions. And it's also really a deal breaker for safety critical scenarios, such as in medical imaging settings. So what I'd like to talk about today is what we should do about this, and specifically some paths towards technical solutions. I don't know exactly what the answer is here, but I think that there are some things that we can do from the technical standpoint to try to address this problem. The first is to build tools for people to try to be able to detect model-generated content. The second is to help models better know what they don't know. And the last is to actually try to improve the model's predictions in the first place. And as we go down this list, we get more powerful tools, but the kind of tools that we're trying to build here get harder and harder. Now, I don't have time to talk about all of this, and so I'm going to focus on the first two. And I'll first by just briefly mentioning some of our work on trying to detect model-generated content. The idea here, or the initial idea here to actually solve this problem, would be to try to train another language model specifically to be able to detect if text was written by a model or by a person. And large language models can actually learn very powerful classifiers that can detect machine-generated content. But to do this, you actually would need to spend a lot of time gathering data from the model and data from humans, training the detector. And even when you do that, the detector will probably overfit to specific domains, styles, and languages. And so we're actually going to take a different approach, which is actually to use the source language model itself to try to detect its own generations, and to do so in a zero-shot manner without actually using any training data to try to train it for detection. And our hypothesis is that samples and text generated by the model are in a local optimum of the model's log probability function. Essentially, another way of saying that is if we rephrase the text generated by the model, the likelihood that the model assigns to that text will probably drop a little bit. And so visually, we think it looks something like this, where model-generated content is going to be kind of near the peak. For example, on the left-hand side, whereas human-generated content is not going to be at this local optimum. It's going to be somewhere else on this kind of curve of model probabilities. And under this hypothesis, we can actually use this to detect samples. We can use another language model to sample small perturbations of a bit of text and check if those perturbations actually cause the text to have a lower probability under our model. And if they do, that means that it's probably generated by the model. And if not, that means it's probably generated by a person. And we find that with this sort of approach to detection, we can actually get a pretty good detector. And in comparison to classifiers shown in white and gray here, we're able to get a detector in yellow that matches those classifiers on 2 different English data sets on the top. And when you actually look at harder, more out of distribution data sets like German in the bottom right or medical text in the bottom left, we're able to far surpass these supervised classifiers, which really struggle on this more technical text and on text in other languages. So the summary here is that first, of course, model-generated text really deserves more scrutiny than human authors. And DetectGPT uses a language model itself to detect its own outputs. But of course, it also has some limitations. It's going to be sensitive to rephrasings. It's also pretty computationally expensive. And even though we have some signs that it's pretty good, I wouldn't use this detector in prime time to actually make decisions that affect human livelihood. And if you actually want to try out the detector yourself, we actually have a demo online at this URL, and you can check it out. So now, beyond trying to detect model-generated content, the next thing that we try to look at is whether models can actually understand what they don't know so that they can refrain from making predictions in the first place. And this is actually a really challenging problem. Essentially, we want to encourage the model to be unconfident when it sees inputs that are out of the training distribution, that are beyond what it was trained on. And the reason why this is really challenging is that there's really an infinite number of ways that data can change between training and testing, and it's hard to anticipate the full range of possible test inputs. And so essentially, we're going to not try to solve this challenge itself. We're actually going to try to sidestep this challenge and actually use representative examples of out-of-distribution test inputs. We'll call this our uncertainty data. And the good news is that we only need unlabeled representative examples of these test inputs. We don't need to know what the correct response or what the correct label for these inputs is. And then what we'll do is we'll fine-tune our model both to minimize the training objective, but also to minimize confidence on this uncertainty data. And so essentially, we will be taking the typical training objective and encouraging the model to make accurate predictions on those training examples. And then for this uncertainty data, which could be kind of unlabeled test examples, or it could be mislabeled validation examples, we're going to encourage the model to actually have a uniform distribution over possible outputs for those inputs. And once we do this, we ran a number of experiments. I don't have time to go in depth, but on selective classification problems, we found that this was consistently the best method on 4 different image data sets spanning satellite images, medical images, and natural images. And it matches or significantly outperforms ensembles with 5 times less compute. So it's a pretty compelling method. And so overall here, first, kind of one takeaway that I'd like to instill is that we can't really expect these kinds of deep neural network models to make reasonable predictions on arbitrary out-of-distribution inputs without having trained on them. And our approach of kind of data-driven confidence minimization actually tries to explicitly train for low confidence on new inputs. And I didn't talk about this, but we actually can show some nice theoretical guarantees under some fairly mild assumptions, as well as some competitive empirical performance. Now, looking forward, I also like to mention that perhaps we should actually rethink the whole way that we train language models and neural networks. I talked about a couple of different tools, but kind of this typical approach of just training models to predict next words actually differs a lot from how humans are trained. For example, when humans are kind of trained in the context of the world that we live in, and they're penalized for making mistakes, for making things up, for being dishonest, and so forth. And maybe if we were able to train machine learning models situated in the world where making mistakes has consequences, then maybe they would actually be more human-like and actually care a lot more about things like factuality and honesty. And of course, lastly, maybe we should also figure out how to get humans not to make stuff up, because humans also will tend to make stuff up in a variety of scenarios. Great, that's it, and thanks for your time.